Oh, so yeah, I have a question on this one, and then I also made an equation, and then I tried to graph it, and I couldn't figure out the asymptotes.
Okay. Do you want to start with that one? You want to start with this one?
Um, it's pretty much, it's actually pretty much this one. It just like has different. I think can we just do this one, and then you
Sure.
might help me with that one.
How about that? All right. So in graphing the things, we want to start off by figuring out what we can pull from the equation, which are, of course, these values. So what do we have?
4
Okay.
for A, yeah. Two for D.
2 for D. Good.
W equals pi over 6. Or not W, omega.
Omega is pi over 6. Good.
Beta's half.
Say again?
Oh wait, never mind. Wrong one.
Beta equals 2 pi over 3.
2 pi over 3. Good. And that lets us turn these into the things that we can graph with. So how do we find the period?
Multiply that. Divide 2 pi by pi over 6.
Good. 2 pi over omega. So pi over 6 over, 2 pi over 6.
Which equals 12.
2 pi over pi over 6, which is 12. And then we can get phi. So how do we get phi?
Phi is 4. Because isn't beta omega times phi?
Good.
So it's 4 in the end.
2 pi over 3 over pi over 6. Which is 4. Good so far? I'm going to do this by graphing. We can do cosecant and secant 2 different ways. I'm actually going to do it because the other one is going to be online in a little bit. I did it by using the direct thing. I'm going to do it by doing cosine first, or sine first here. So we're saying that our values over here, we have A was 4, D was 2, E is 12, and phi is 4. So for the sine curve, we're going to figure out where the 0, which would normally be here, will be shifted over by phi. So it will be shifted over to here. This is maybe not, actually, before I go any further, maybe the smart thing to do is to actually change the scale so we have a little bit more room. All right. If we do that, then every tick mark is 2. So the first guy moves over, the 0 for sine moves over to here. Everyone on board with that before I go further?
Mm-hmm.
Okay. Mm-hmm. Some of you are probably muted, so if you're saying stuff but you haven't heard yourself, that is unmuted. All right, and then the next thing is going to be that we move over to, we should probably actually figure this out somewhere. What are our max and min values?
6 and 2.
For the sine. How'd you get that?
It's A plus D and A minus D. For max.
So it's actually D plus A, which of course is the same thing, which is 6. But
and then
minus A.
Oh, okay.
All right, so we get, because we need it to be 4 between the midline and whatever. So our midline is going to be here. So my 0 is actually going to be not a 0, but the value of 2. And then a quarter period later, I should be at my maximum. So a quarter period is 3, which is 1.5 tick marks. So something like that. And then a quarter period after that, again, I should be at, I should be back at 0. So that would be here. And then quarter period gets me to my, Oh, I'm sorry. The max is 6, not 4. So it should be more like that. And then min is -2. And it should be something like this. And then back to a 0 here. And that is 1 period later. So that's good. And then I guess I'll go backward in time and do it the other way so that I can get the second cycle in.
Yes, you can.
So my sine curve will be relatively steep. It will look like this. We weren't asked to graph the sine curve, but we can use it as a skeleton. We were asked to graph the cosecant, which will have asymptotes everywhere that the sine goes through the midline. So asymptote there, asymptote there. Oops. That one's entirely wrong.
So that, like, for all of the ones where it's like inverse, like a cotangent, cosecant, and secant.
All of the reciprocal functions will have asymptotes.
And tangent as well.
And tangent, because tangent has the cosine on the bottom.
All right.
Is the asymptote always where it goes through the midline, or is that only for cosecant?
Yeah, because where it goes through the midline is where the sine or cosine is 0, and the reciprocal function is 1 over that.
So we can just write stuff like this and like show, and then like, so we could pretty much draw the graph and then just show asymptotes.
Yes, as is not uncommon, people are asking questions before we're finished. So now it's not clear if you know that we're finished. So let's actually because we still have not drawn the cosecant.
Oh yeah.
Recognize that? So
yeah.
Before we start talking about how we would play around with it, let's actually get the cosecant on the graph. But it's easy. It's going to share these points. And it's going to run away towards the asymptotes everywhere else. So asymptotes do for us.
Who's like slamming a bowl against a wall?
No, they're eating.
Ah! It was so loud.
Okay.
That was so loud.
All right. So our cosecant curve is this curve.
Gabe, you kill me.
No. I need to lower the volume, dang.
Or stay away from the mic.
Sounds like someone slammed a bowl like right against their mic.
All right, I forget who was asking at the start, especially about the phase shift. Are we okay?
Oh yeah. Should we like be able to name, like when we're drawing the asymptote, should we write like what they are, like x equals and then the asymptote?
You aren't required to. If it says to graph it, you can just graph them.
Okay.
Once you've marked them down, it's pretty easy to come up with their equations, but it's also going to be true, at least for the sine ones, the asymptotes will be at phi plus n q over 2. Yeah. Right, they occur every half period because they occur where sine is 0, and they'll be shifted over by the phase shift. For the secant, it would be something similar, but we'd have to figure it out. We'd start off a quarter period over and then be shifted over by the phase shift.
Wait, so what's n in that equation?
Any integer.
Okay.
Wait, what does that equation show? I'm confused by that.
That's where the asymptotes are.
Oh, okay.
Right. The asymptotes start off at the phase shift because they start off in a regular secant or cosecant. They would start at 0, so they're shifted over by the phase shift, and then they're every new one based by half a period.
What's this?
So not a quarter period, half a period, or does it matter?
Okay, it's a half period because we want to go from when sine is 0 to the next time that sine is 0.
Oh, okay.
At the quarter period, we get the other special points. We get the max or mins.
Okay, that's all right then.
Steel isn't strong, boy. Flesh is stronger.
What is going on right now?
Sounds like blasting
It
that.
sounds like people have some other stuff going on in there.
Yeah, turn off the TV.
Can we do number 8 on the review packet?
Sure.
Okay.
Guys, I'm on the thing. Can you lower? Mom, can you lower the TV volume?
Mr. Gupta. Classic.
I should turn it up and just lower it.
All right, what values can we read from a graph?
D is -2.
What?
Okay.
Yeah.
That's a good one.
Because it's how far it is from 0, not how far it is from the top.
Is the amplitude 6?
Amplitude's 3.
The amplitude is 3.
Oh, yeah, 3. That's what I meant.
Okay, well, before tomorrow, you should figure out the difference between 3 and 6. What else can we read from a graph?
The period is 5.
You can read the period, which looks to be 5, right? It's a little bit more than 1, so a little bit more than 6. So it looks like it's 5.
Okay. The maximum's 1 and the minimum's -5.
We can do the maxes and mins.
I don't think there's a phase shift because
Yeah, because it's the midline goes through 0.
Good. There's no phase shift because it's already rising through 0 right there.
So beta equals 0 and phi equals 0.
Right. And then once we have that, now we can turn these things into other values. So we can say that omega is 2 pi over p, or 2/5 pi. And this we can turn into saying beta is omega phi, and therefore is also 0. So y, which is a sine omega x minus beta plus d, becomes 3 sine 2 pi over 5 x minus 2.
Could we make up a problem that's dealing with cotangent?
Wait, I have a question.
Uh-huh.
So could we also make equations for cosine of the graph? Or?
You could do that, but the directions,
Yeah, but we should be able to do that.
you should be able to. That's fine.
Oh, so what would that be? How would that differ?
Okay. So how would that differ?
Isn't the period midline?
No, period would be the same. Only thing would be the phase shift.
Yeah.
I guess phase shift would be 1.
All right, so we have a minus 2 and 5.
Oh, because the phase shift is measured.
Yeah, it'd be 1.
But now the
How do you
phase
know
shift-
that's 1?
Let's
You
be a
measure
little
both
bit more than 1, to be honest.
It would be 5/4.
Yeah, it'd be 1.25 or something.
Yeah.
Mr.
Oh.
It's probably going to be, to be honest, it's probably going to be some fraction of the period. It's going to be 5/4.
Oh, it'd be you move over a fourth, right? So yeah, it would be 5/4.
Quarter period. It's a quarter period over.
Yeah. Yeah.
And then you could say 3 cosine. I guess we have to get it. So beta would be 2/5 pi times 5/4 or pi over 2. So it'd be cosine 2 pi fifths x minus pi over 2 times 2.
Wait, for the sine curve, how do you know the phase shift is 0?
Anyone want to chime in?
Because it goes through the 0, so a normal sine curve goes
It's
through.
rising through the midline at 0
Whereas for
Oh, okay.
for the sine.
For a cosine, it would have you measure from tops, correct?
For the cosine is going through its maximum at 0.
Okay.
So you have to see how much that shifts. You're always identifying what is the x equals 0 point, where has it ended up? That's what the phase shift does.
So for this, I'm confused with the difference between if you shift it forwards or backwards, because that was on the homework too. But
there is no difference. You could easily have said that this point has shifted over to here, right? How far is that?
5.
Which is
-5.
shifted by a period.
Oh.
So you would get 2 pi. Beta, you'd get 2 pi. And then you'd find that it's, right? By convention, the phase shift should be between 0 and less than 1 period. But a phase shift of minus pi, or minus pi.
Could we do an equation with cotangent, like finding and graphing cotangent?
Yeah, that's
Because like tangent's definitely a little confusing, just because of all the special.
All right, Mr. Schiffer, give me the problem you want to do.
So y equals 2 cotangent. I guess 2 over 5x minus pi over 3.
2/5 x.
Pi over 2. Yeah, 2/5 x minus pi over 2. Plus 1.
bruh.
All right. What can we identify from the equation?
Amplitude is 2. D is 1. Period is, well, solve that.
Omega is 2/5.
Good.
Oh, yeah.
Beta is pi over 2.
And beta is pi over 2. What can we get from omega and beta?
You can get the period from omega, which is 5 pi.
How come? Don't skip the
No.
pi.
It
Well,
would be
2/5 p is equal to 2 pi.
no, but
multiply-
it's
Or
pi.
5 pi over 2.
Oh.
It's pi, not 2 pi.
All right, but it's cotan, so it's pi.
Yeah. Oh, my bad. What's an L?
Wait, why is it pi for cotangent?
Because tangent and cotangent are twice as frequent as the equivalent sine or cosine.
Oh, so you don't make, so the formula isn't omega period equals 2 pi. It's just pi.
No, it's omega period equals pi. And how about phi?
You get pi from beta over omega.
Okay, and that stays the same.
Yeah.
What is that going to give us? 5 pi over 4?
Yeah.
Anyway. Yeah, okay. All right. All right, so we'll need a graph. Our period is 5 pi over 2, which is not particularly wonderful. So maybe we'll make all of this I'm going to rescale the graph again. 5 pi over 2. If this is 2 pi on the right period, so let's call this Should we just call this 5 pi? Okay.
Yeah.
All right. So where does tangent, what is cotangent doing at x equals 0? The unadorned cotangent?
It's going towards the asymptote.
It has an asymptote. So we're going to shift that asymptote. I'm going to shift it over by this amount. So every one of these guys, these boxes are pi. So 5 pi over 4 is something like this. So that's our first asymptote. Where's the next asymptote going to be?
5 pi over 2 later.
Good. So we're going to be at 5 pi over 4
Up here, yeah.
plus 10 pi over 4. So I need 15/4 pi. So that's 4 3/4. So our next one's going to be something like this.
Wait,
Why-
why is it 10
Yeah.
pi over 4?
It's shifted
Because you
over by-
converted.
Oh, it's the phase shift plus.
It
Period.
starts out here. That's the first one. And then the next one's 1 period later.
Oh.
Where's the next one going to be?
Well, you could go backwards, like negative 5 pi over 4.
Okay.
25.
It's going to be minus 10 pi over 4, so it's going to be negative 5 pi over 4.
So we'll have one at negative 5 pi over 4, which is like this. No.
Yep.
Yeah. No, my spacing seems a little weird about that. Don't worry about my spacing there. Did I do the right? I'm worried about I worry about this spacing here. Yeah. All right, it should be another 5 pi. It should be this distance over again, right? Now I'm going to get myself a little confused. That's 5/4. And it's 15.
Should I just change the? Should we change the?
You can change the scale.
Or like the? Should we change A from like 2 to 1? Is that what's messing it up?
No, I haven't even looked at A yet.
Yeah.
A is a vertical shift. A doesn't do anything to where the things occur. Right? I'm just doing some arithmetic in my head that's going a little weird. If I want to go, it should. What's messing me up is the next asymptote should be this far over. So it should be something like here. Right?
Mm-hmm.
But that is, oh yeah, it was my arithmetic that messed me up. It's not 4 1/4, it's 3 3/4. 3 3/4 is here. Yeah, that's believably close.
Mm-hmm.
Those are about right. All right. And then 25/4 is 6 1/4. So again, that's believable. And the other is going to be at minus 1/4. 1, 2, 3 3/4. All right, that'll give us 2 cycles. So it's probably good enough for now. All right. What happens halfway between the asymptotes?
Oh, the
graph.
inflection.
Yep, so this whole thing should be 0 at that point. Right, halfway between the asymptotes, the trig function is 0, but we have d. So we'll be up at 1 halfway between. Now halfway between these are going to be kind of annoying, so I'm going to eyeball them. Right, one of them would be here. And then I know. I'm kind of eyeballing them to be halfway through. I should calculate them, but the quarter is throwing us off. The scale is not great here.
On a test, if we like draw it roughly to this.
Yeah, this would be, so far everything we've done is certainly within reason. And then we should decide, the next bit that's tricky is how to sketch the amplitude. All right?
Should we change the amplitude? Just because that's like not really going to be applicable.
So I'm not going to worry about it when I sketch this. I will tell you that on the test, this will always be just 1 for tan and cotan. They're very hard to read. They're very hard. They're annoying to read, annoying to get right. What we have to do is figure out where the quarter period thing is, because the value for cotan is A is whatever is happening 1/4 period past the asymptote.
So like.
So 1/4 past the asymptote should have a value of 2. So it should be something like this. And then.
Wait, so why are we drawing it there?
Value of 2, so it should actually be up there. It should be 2 higher, and it should be 2 lower. So we should pass through like this.
How did you figure out where the midline was?
Because that's where
the midline.
Yeah.
So
I
figured out it's shifted. Normally it's 0, so all the zeros are shifted up 1.
Oh, okay. So the reason why that's at 1, the reason why those are, it's always going to be a quarter in between. It's always going to be halfway in between the inflection point, and the asymptote.
Right. So the value. Okay. So if you in an unmodified tan or cotan, all right, the zeros occur halfway between the asymptotes.
Mm-hmm.
And that halfway between those two, which is 1/4 period, the tan and cotan have a value of 1 or -1. Now here, instead of having 1 or -1, because we had the value of 2, it would have a value of 2 or -2. So I go either 2 up or 2 down. I go either 2 up or 2 down. So if I want to sketch it nicely, I got to go through here. Although it's fair to say that this is sufficiently tight that it's hard to actually really tell that I'm even using those points. And that's okay, because you're just doing a hand sketch.
Wait, so how is like the graph of tan x with all of the same like a, d, like omega, how is that like different from this graph?
Well, for one, now it goes away.
Okay.
Right? And it would be shifted over so that all the green lines would be where the zero crossings are. So if we want to, I mean, it's hard. It's a very busy graph, so it's hard to show more on it. But it would look something like it would go through zeros, or it would go through the zeros here. It would
but wouldn't that make phi like different?
No, because phi is the same thing. So now instead of this asymptote would be where the 0 would move to.
Everything would just shift over, like half a period?
Everything would shift over, but of course the direction of the curve would also flip.
Wait, so what would happen if what was what?
She asked if it had been tan instead of cotan.
Oh.
So a tangent would pass through there, and these would be asymptotes. So it would look something like that.
Oh, okay.
All right, where there are asymptotes would become zeros, where there are zeros would become asymptotes. Got about 9 minutes left in the session.
Can we do number 4 on the review sheet?
Sure.
And so direction would flip, and it would like shift over by a half period?
Yeah, so that's the difference between tan and cotan. All right, what's our base function?
Tangent.
This is a tangent function of some sort. What can I read from the graph? All right, there are always 4 things you can read from the graph, or 4 things you can get from the equation.
So it's tangent.
Yes.
Yeah.
First and foremost.
Wait, how do you know it's not negative cotangent?
You don't.
Oh, okay.
You can model
There's no-
tan and cotan, and you can do a sign flip. But just sign flips only just introduce phase changes. So if you wanted to model this as minus cotan, you could do it, but it would be weird. Doesn't make your life any easier, though.
So asymptotes are too apart from each other.
Looks like one there. And so distance of 2. I guess I believe that. Yeah, I believe that. What is that? The distance of 2. Which of our variables?
Isn't that half the period?
It's the period. All right, if you want to look at it this way, this 0 is 2 or so away from that 0. In fact, it's not really 2, it's 2.5. Which means I would believe that this is actually not quite 2.
It's like 2.5.
It's 2.5. I'm going to redraw those later anyway, though. All right, anything else I can read from the graph?
Is the phase shift 1.5?
How come?
Because from 0, it's over by about 1.5.
Good. Tangent would have passed through that point. This guy's passing through that point. That's phi. This distance, sorry.
Is it like 1.5?
This distance is p. So it's 1.5. So phi is 1.5. How about A and D?
A is always 1 and D is 0, right?
Well, A is 1. D doesn't have to be 0, but in this one it's 0. How can we tell?
The inflection point.
It's pretty even.
Yeah, it's symmetric above and below the x-axis. The inflection point is occurring on the x-axis. Now I can get omega and I can get beta. How do I get omega?
2.2 pi over 2.5, right?
Well, pi over
Pi over,
2.5.
pi over 2.5, which is what, 2/5 pi.
0.4
Yeah.
pi, I think.
Okay.
And beta is? How do I find beta? Let's always jump to the
3/5 pi.
How do I find it?
And what?
Beta.
Omega times phi.
Is omega phi. So it's
2/5
pi times 3 halves.
3 halves.
So it's
3/5 pi.
So our equation is going to be y equals tangent 2/5 pi x minus 3/5 pi. I guess plus 0, but we don't have to write that.
How did you know the amplitude was 1?
So I didn't here, although I can check it out. It's going at a quarter period, which would be what? Quarter period is like 0.6 further. It's going through, right? That's about a quarter period. Right? We have it, and we have it again. And notice it's going through 1, where the value of the quarter period is your value of A. Is your value of A plus B. Tangent starts at 0, and a quarter period later goes to 1, and then goes up. So, just like with the sines and cosines, what you care about are the special behaviors, and the special behaviors happen at quarter periods. For tangent, the special behaviors are 0, the value of A, asymptote value of minus A, and then 0 again.
Could you give us an example of a problem that would like do odd and even functions?
Sure. What do you know about odds and evens?
So odd functions are like f of negative x is equal to negative f of x. And then even is f of x is equal to f of negative x.
All right, traditionally written that way, but it's fine. What's the graphical equivalent of these, right? These are algebraic statements. What are the graphical equivalents? They're both symmetries. for instance, if I graph this, okay. What kind of function is that?
Even.
How do you know?
It's symmetrical about the x-axis, the y-axis.
Good. This has symmetry for reflection about the y. No, it's not really a function. What kind of symmetry is this?
No symmetry about the x.
Y. It's like
what kind of function is this? Odd or even or neither?
odd.
Odd.
How do you know?
It's symmetry
About the origin.
Good. It's symmetric for rotation around the origin. That when we went over some distance here and went right over x and up to y, then when I go to the same distance this way, I go down instead of up, and I hit it again. And that's true for every point. So that's the same as saying that's been rotated, and you can spin it about the axis, about the origin. So you might be asked to identify graphs, or you might be asked to do, right? You know that we had the homework problems about showing sums and differences in products and so on of odds and evens, and seeing if they have special properties.
Wait, so sums and differences in products, could we just go over that? Because
yeah.
Okay. What type is quotient? Oops, sorry. Up to even functions.
Quotient. Okay.
We'll assume they're defined, so we're not going to get any kind of weird. Ignore the idea that they might be zero on the bottom. So where they're defined is correct.
Wait, shut up.
Kai, is that your younger brother?
Yeah.
Okay, so let's define
Let's focus though.
our quotient. How would I see what happens, what kind of symmetry the quotient has? How do I tell if a function's odd or even?
Oh, you plug in negative x for x. You substitute.
Right? And then direct substitution gives me this. But f is even, so what does that say about f of minus x?
it's going to be the same as f of x.